Um, so first, like, I think maybe we can kind of do like a little bit of just like what are hubs, what could you potentially use them for, why do we need a different data structure for them versus just being able to use existing data structures. And then we'll get into some kind of like tips and tricks and like how you can avoid some potential pitfalls and get you set to use the actual version in your own code. So the basic idea here is that you may already be familiar with, we've got this ZO data type called a queue. And so maybe we can do like a really simple example here of we'll make a queue. And we make a queue using this queue dot. And there are actually a couple of different constructors for different types of queues. There can be bounded queues or unbounded queues or sliding queues or dropping queues. And I mean, maybe if we want to, we can spend a little bit of time on those different variants. But right now, I'm not going to worry so much about the back pressure aspect. And then whenever we make one of these, we got to give it the type of the elements that are going to be in the data structure because it kind of starts out empty. So it doesn't naturally have a concept of like what its type should be. It's not like you make a list of ints that kind of knows from the ints you put in that it should be a list of ints. The queue starts out empty, so you need to just tell it what type of queue it's supposed to be. And then the bounded one in particular takes this parameter for how big the queue should be. And I think there's a nice note here that when possible, we should use powers of 2 for the capacities. So I will not use 10, I will use 16 instead. And so we've made a little queue here. And then in terms of like when you would use queues, a lot of times these will be buffers between some concept of like a producer and a consumer. And so maybe we can actually even like define some little processes here to be our like producers and consumers. And so maybe this producer is going to have some reference to a queue that it's going to work with. And maybe initially we'll, well, let's have it, let's just run a couple times maybe. So maybe this will be a ZO, any nothing unit. And maybe initially we'll say something, maybe we'll go with 10. This is not bad. There's no need for people to die. Thank you though, Copilot. And yeah, maybe we'll sleep. That seems like a wonderful idea. We'll sleep for 100 milliseconds after that. And I can do for each discard, select more efficient. And then I need my clock in my environment here. Okay, so I've got this kind of producer that's going to just every 100 milliseconds offer a value to this queue. And I mean, this is kind of very simple, but we can think of this as like a stand-in for we have some maybe push-based interface that just every 100 milliseconds is going to send us the latest Twitter data or whatever. And then we'll have a consumer here. And so maybe this consumer is just going to take a value from the queue. And so it's going to get this measure. And maybe initially we'll just have it like print out what it got. So we'll just say print line, consumer got I. And then we can just call this thing forever. Let's tell this guy to just keep taking values from the queue as long as there are values to take. And so now that we've got our queue here, I think I have to like tab to do that. And wait, what do we got here? Nothing, because this is never going to complete. And console. Let's see. Oh, and I will do the or die. Yep. Okay. So now that I've got my queue, I can create this producer, and I'll fork the producer, and maybe I'll return a reference to this fiber, and then I'll make my consumer. And then my consumer is never going to be done, but my producer is eventually going to be done. So maybe I'm gonna wait for my producer to be done. And then at least for us to have a little example here, maybe I'm gonna wait another, I'll just wait a second just to make sure everything's done. And then I'm going to interrupt my consumer and I'll be done.
Oh yeah, I call them fibers just to
just to be a little more explicit. That sounds lovely. Okay. So I think we're ready to run a simple example here. So let's try this. See what we got. Okay. And so we see that the consumer got 0 through 5, which I did 0 to 5. We did 0 until, then I'd only get 0 through 4. And we see that the producer put each of the values in the queue, and then the consumer got each of the values from the queue. And in this case, just printed the console, but we can imagine in a real case, it would do something more sophisticated with that. And so you'll sometimes use queues directly. Queues are also used a lot internally in the implementation of streams, both in some stream operators, as well as if you think like at a more basic level, a queue is basically what you have anytime you go between a push and a pull based interface, because those are like these two different protocols. And so you got to have something sit between them. And the queue is basically the thing that sits between them. So the distinguishing factor of this queue, or at least one of them, is that every time you take the value is not in the queue anymore. It seems kind of obvious, but like we'll see in a sec why that's like significant. So we can imagine, okay, here we had one producer and one consumer. So let's like create a second one. And yeah, we could just copy the method, but I think that's probably a more composable way, or we can create a consumer with an ID here. And so then maybe I'll put consumer 1 fiber. And then we can make a second consumer fiber here. And let's try running this guy. Okay, and so if we look at this, we say consumer 1 got, in this case, 0, 2, 4. So it got 0, 2, 4, and the other one got 1, 3, 5. So in this case, it was one got even and one got odd, but that was like completely like arbitrary here. Like that is not necessarily deterministic, but we can see that each of these values only got taken by one of the consumers. And in some cases, that could be exactly what we want. So like we could imagine maybe these are like incoming messages and we need to do some kind of like decryption on them. And we're just trying to maximize the performance on our computer. And so we've like maybe we forked 16 of these because we've got 16 cores on our computer. And so each one is just going to take one message and decrypt it and send it wherever it needs to go. And then this is like the perfect thing, right? That like we only need to decrypt each message at one time. And that's exactly what we're doing. And we're getting some parallelism built in here. So like this is a nice way to do. Sometimes you could describe this as like the as a problem of like distributing work, right? Of like you want to split it up between different processes, and you want each piece of work to be done by someone, but only to be done once. And in fact, this a queue is actually used internally in like some of the bounded ZO parallelism operators of like, this is kind of how you would do like for each par n or collect all par n. If you kind of wondered how that was implemented, you essentially create a queue and then you create X fibers that just take values from the queue and just keep taking them and processing them. So for like that use case, this is great, but we could kind of imagine another use case where, and maybe we can like make this more clear if maybe like instead of making that a int, we make it like a string. And we could imagine maybe consumer 1 is like, I don't know, let's just call it like a logging framework. And let's call number 2 maybe like the database writer. So we could imagine now that this producer is like sending events into the system. And we've got these two different processes, one of which is supposed to log the events to whatever logging framework we're using, and one of them is supposed to persist them to our database so we have them on the longer term. And so now if we kind of run this program, and it's basically the same program, it just has different labels, but now this really isn't so good for us because we've accidentally ended up writing only half of the things in the database and logging only half of the things. So this isn't really what we want to do here. And now the scenario we have is kind of, it's the opposite of what we had before. We don't want every piece of work to be done only once. We instead want every piece of work to be done by everyone. So yeah, so broadcasting is another word that you can use for this here. And so the simplest solution, you might say, and it was kind of what people did if they had to do this in ZIA 1.0 before like the actual hub was developed, is we could actually kind of implement our own, maybe we call it like a naive hub here. And this naive hub is just going to basically be more than one queue. So maybe we make this like a chunk of queues. Maybe I'll give that a type parameter exactly. Chunk of queue of A. And there are a couple more offers, but really there's only kind of two fundamental methods that we used here, right? We were just taking values from the queue and we're offering them. So those are really the only two things that we need. And so if this is our representation, each of these can actually be pretty simple. Of if I want to offer something to this hub, then I just offer it to each of the queues. And when I take here, so take is actually going to be slightly different here because we're going to have some concept of like a subscription, you could say. And one way we can actually represent the subscription is this queue you can only take from. And let me kind of build up to that a little bit. So instead of having take here, and maybe actually initially I'm going to make this even simpler than this. I'm going to have this take like an N. That's just going to indicate which of these queues we want to take from. And so then this is going to be super simple. All we have to do is take it. We just have to index into this chunk, and we have to, yeah, it's just q sub n exactly dot take. So that's super simple. And then all we have to do here is we just have to implement a constructor for our naive hub. And let's initially, we're going to even just hard code right now the size of the bounds of kind of how many we're going to back pressure, but we're just going to specify how many subscribers we want to have here. And so all we're going to do is for each of these, we're going to make a queue. And then I don't think we're going to need that. And then we're just going to put that inside our naive hub thing. Let's get some auto compilation going here and see what we got going on. Oh, so this we can just, I think we just need a unit there. Oh, use discard, perfect. Let's see what else we got here. Oh, this is going to be a.
I think you just need to do two chunk or chunk.from iterable. Get that in the right shape there. Oh, almost, not quite.
Found abstract.
Nothing collection abstract seek of thee.
I think we're just missing a parentheses here.
That's possible.
I believe. Let's see.
Ah.
Okay, so I'm just going to make this. Let's see, I can just do
chunk. Yeah,
chunk from iterable. Okay, and now we found the chunk of queues. Oh, so now we can just get rid of this.
Okay.
And let's see, is this found chunk of, oh, and these need to be use of A because we want to be polymorphic. Okay, so now this is compiling. And so now we can try using our naive hub here, and maybe I'll leave this for us for a sec. So maybe we can call this like Q example, and then I'll just create another. Oh, sorry, what's that?
To simplify it slightly, can we remove the consumer fibers just to have it be so we can fit more on the screen? Because these will be canceled automatically, right? If they're forked, and then this scope exits.
This finishes. Yeah, we should be. I think we should be fine there. Yeah, I was probably doing a little bit of belts and suspenders there.
Gotcha.
Oops. Okay, so now we'll do hub example. And so we'll just change this to be a hub. And we'll do, we'll make this a naive hub make. And this time this int is going to be, we're going to have 2 of these. And then we're going to need to update these. So why don't we, maybe I'll make copies of these. And I'll maybe call this like hub producer and hub consumer. And these will take our little naive hubs. And so I think the hub producer is going to be quite similar, except I'm just going to replace Q with hub there. And the hub consumer is going to need slightly more because it's going to need this index. And we're just going to pass it down there. And I think otherwise we'll be good to go here. And then we can go down to our example here. And so now we'll make our hub. Then our producer fiber will be hub producer, not the naive hub. And these 2 will be hub consumer, hub consumer. And then let's see, what are we off on? Oh, right. And then we actually need to have a run method somewhere. So say val run is equal to naive hub example. Yep, let's avoid blowing up with all initialization issues. That's lovely. All right, so now let's try our naive hub example. So fine.
Yay.
And so now we see that, okay, well, we can just check ourselves here. So they both got 0, they both got 1, they both got 2, both got 3, both got 4, both got 5. So this is kind of what we would want in this type of situation where we wanted to broadcast this work, right? We wanted to broadcast these incoming messages for different people to work with them. And in some cases, it may be relatively few people, like here there were only 2. But in some cases, maybe there are 10,000 or maybe there's 100,000. So in some cases, there could be very many different people who are consuming from this and who all need to get the same information to go and do something with it. Before we go on, any questions, folks?
We have a couple in Discord.
Yeah.
Except I'm not sure exactly when this was asked. So
that is the danger.
Why not streams with subscribers? And then what's the thing provided by Hub that makes it better than a stream for this use case? Is a Hub a finite stream? And I think maybe we should wait on some of those when we get to the actual Hub implementation.
Yeah, well, and maybe I can just do a little bit of, so like, because I think a lot of those questions are really getting at like streams and how streams relate to hubs. And I think the basic answer is like streams relate to hubs in the same way that streams relate to queues. And that's that hubs and queues are concrete data structures that are used in some implementations of streams. And so I think that when you're asked that question, that's completely right, that like both of these examples could be rewritten in more of a stream first format. And maybe that's something that we can do down the road. I'm not that far down the road, but like within the next hour. But I kind of wanted to just see like what these were at a more basic level first before we layer on the streams, because we layer on the streams with either the queues or the hubs, depending on the stream operator. And we can definitely produce the same output and maybe in a little bit more of an elegant or compositional way. But that operator is internally going to kind of use these data structures, but not necessarily show them as much. So I think this is probably a good way for us to get started with these, and then we'll go to the streaming as we progress here.
Mm-hmm. There's another question that is more about like a stream tip, so I'm going to save that until a little later, if that's all right.
Yeah.
And then Phil Allen observes that RabbitMQ topics resemble native hub. Topic just multicasts, and each subscriber, a set of competing consumers, has to have its own queue. So yeah, I think this is a fairly, like, we said naive hub, but it's not an uncommon architecture. And I think this is sort of, this was at least an implementation that was used in FS2 at some point. I'm not sure if it still is.
Yeah, that's right. I think at least to my understanding, it still is. And yeah, in their case, they call it, I think, their topic data type. And that was a little bit of part of the motivation, I think, in Zio for having this, was like we had people who, like, they were coming to Zio streams from having used other streaming frameworks, and we're naturally kind of looking to replace the things they had with the Zio equivalents, and we didn't really have a equivalent at the time. I mean, as you can see, and like in a way, it was like not that hard to do. But one of the things we wanted to do is really, when we did it, we wanted to do it the right way from our perspective, at least. And so I think that's a nice segue to like why I use this term naive hub here. And it's not just because it's not the exact version in Zio, and like maybe there are some more operators, but the implementation is actually pretty fundamentally different, where there's an inefficiency here, where every time I want to go to offer, I've got to like go to each of these queues and like drop off the value in it. And this queue itself is like a really highly optimized data structure. Like if you look at the implementation of this, like they are counting like how many concurrent swaps can I like get down to, and it's like 2. And they're like, can I make this set a lazy set instead of a set? So this is like super optimized. But if like I have, let's say, like 10,000 like consumers here, and like I saw examples of this before we did the development of this, like, okay, when you kind of multiply that by 10,000, like your little, did I do 2 or 3? It kind of gets dwarfed by the fact that you're multiplying it by 10,000. Mm-hmm. And there's like 1/2 of that that's a little bit unavoidable, of like every time you take, you've got to update some kind of piece of state that's specific for like that person, because like they've got to update their index and not anyone else's index. But if you're offering, one would think that you should be able to do better than just dropping it off in 10,000 different mailboxes here. And that's basically like the motivating idea behind the hub data structure, is instead of having all of these different queues, can we essentially just have one queue or one data structure underlying the queue? And so the queue internally is actually backed by an array, and then you have some atomic variables that kind of indicate your indices into the array. But so if I can do very poor like ASCII art here, and then maybe better at this I am, but like if we have the naive hub, we can think of that as, okay, I've got this Q1 and I've got Q2, and here I think in the real one where they had 16, but I don't know if I want to do 16. But you had these 2 queues that each had this array sitting behind them. And then you would have some values that got popped into the queue. So let's say we're like partway through, and we've got like 2, 3, 4, 5 here, and maybe this consumer is a little bit ahead, so it's already gotten 2. And you've got 3, 4, 5 here. And so like very naturally reflects what we did above here in code of every time I want to put a value in here, I just go to each of these. And if I have 10 of them, I just go down the list. And if I want to put in 6, I put 6 here, and I put 6 here, and I put 6 here, and I just put 6 however many times I have. And if I want to take a value out of the first queue, then I just take 2 out of here. And so just saying that again reflects this like seemingly inefficient work we're doing of like, I only had 1 6, but like if there are 20 of these different queues, I'm putting that 6 in a queue 20 times, there's only 1 6. So you can say, well, I'm like, okay, could I do a little better than this? And so the idea of ZHub is like, what if we only had 1 hub? And so we had the single array. And that was nice. Good job, Copilot. And so now let's say we have like the same data in here, but now I can just keep track of like only a few other pieces of information. And so to like slightly simplify, I could just say consumer 1, their index is equal to, we say this is 0, their index is equal to 1. And consumer 2's index is equal to 2. This is the place they're supposed to read from. And so now we've gone from having n of these arrays that are underlying all of this to having 1 of these arrays. So much lower memory footprint and much lower work when we offer a value to this hub. And so that's basically like what differentiates the actual ZHub from this naive hub. The actual one has some more operators other than just these 2 we implemented here, and it's got some more variants, and it can be just like the queue, it can be bounded and sliding and dropping and unbounded. But like at a basic level, this is what makes the actual hub different than the naive hub. And so at this point, we can actually probably take this example, and maybe I'll just make it our like hub example here. And the process will also see a couple of like a little bit, call it complications run into, just because this is actually trying to be like a little bit more production grade and a little bit more safe. So we're going to make the hub. And there's one other slight difference between the actual hub and this naive one is this naive one had a static number of subscribers, right? When we created the hub, we said, well, this hub has 3 subscribers. And for this little example, that was fine because we could just, we knew we were just playing with this like database writer and logging framework, and so we just put in 2. But in some production cases, that doesn't really have enough power. So we want to be able to dynamically subscribe and unsubscribe and have that change over time. So here we're going to make this hub, and then we've got a couple of these consumers here. So, and now I guess I got to update my little hub consumers. And so my hub consumer. And so because we have this dynamic aspect, the hub has this subscribe operator that says, hey, I want to subscribe to now receive messages from this hub as they become available. And it's like, I guess it's slightly cut up, maybe a highlight here. There we go. So the couple of interesting things we can see about this is, one, it returns a Z managed value. So whenever we see a Z managed, we know there's some finalization associated with this thing. And in this case, the finalization is that when this scope ends, we're going to unsubscribe from the hub. We're going to say, hey, we're no longer interested in receiving more values from the hub. And that's important because when we have this type of representation here, at least if it's a bounded hub, we need to know when it's okay to drop the last value. So like here, let's say that this is a bounded hub and it only has this many spaces. So you want to offer 6, okay, fine, we'll put in 6 here. You want to put in 7 here, but let's say you want to put in 8. We need a way to know, is it okay to overwrite this 2 and put in 8? Or do we have to back pressure at that point? Do we have to say, hey, the hub is full, you've got to hold on until there's more space available? And the way we answer that question is by saying, has everyone who's subscribed taken that value from that index. And that's where unsubscribing becomes important, because if you've subscribed and then you just stop taking values and just sit around and you never unsubscribe, then the hub is kind of holding that space for like you eventually wanting to take that value. And so that's going to potentially, if you're like have a hub that's back pressuring, it's going to stop other consumers from being able to take those values. So that's why you want to unsubscribe, and that Zmanage will take care of that for you. The other thing we can look at, it's kind of interesting when we look at the signature, is it returns this DQ thing. And a DQ is kind of interesting. A DQ is actually, it's just a subtype of a queue. So all the operators that you use on a queue, you can use on a DQ, and you can use a DQ where you need a queue. The difference is just that you can't offer to a DQ. You can only take from it, which makes sense with a subscription of like, you've subscribed to receive values. You can take values as you want to take them. You can't put values into it. This is just a source of values for you. So here we're going to subscribe to the hub. And then, so here we're going to flat map. We could also just change this to being use. And get rid of the use now. So we're going to subscribe to the hub, and it's going to give us this resource of the queue. And then we're going to take from that. And each time we take from it, we're going to print this out. And then the producer, we just have a very slight difference in terminology if we just call this publish. So now we've got the producer and the consumer going. And so now we can go down here. Let's see. So this is going to be a hub.bounded. And now this is going to, again, represent the size of the hub. So it's going to be just like what we were doing with the queue. And then
not the number of, before that number was the number of total subscribers. That is now
exactly
dynamic. Now it's
exactly. Yep. And we won't need these numbers here. Yep. Okay.
Cool.
And so now we're compiling here. Now, this is where I'm going to kind of show you one of the things that, particularly when you're doing these test cases, you want to watch out for a little bit. And that's the order of doing the subscribing versus publishing. Because part of the way that we're making sure we're like safe with our space here is we're only going to give you a value if you've subscribed when a value is published. And so if there's no, like let's say the extreme case is no one subscribed yet and we published a value, well, that value is kind of going to get like thrown away because there's no one who said like, hey, I'm interested in values yet. And at that point, we have no way of knowing like at what point would we remove that value, or what point would it be safe to overwrite that value. So what we want to make sure we do, at least in these simple test examples, is we want to make sure that we've got our consumers subscribed before we start publishing. In production cases, that tends to be less relevant because we're typically dealing with these asynchronous processes where we just want to pick up with events wherever they left off. So like if we go back to that like very first thing we did with the Zio Slides app, we had some kind of server that was producing events. We had clients that were like receiving events. And I mean, these were obviously like over the entire internet. So you might have access to this web page at any point in these events, and you just wanted to pick up the latest events and start doing things with them. So in those cases, it ends up being less important. But in these simple tests, one of the kind of watch outs you want to have is you want to prevent that race condition if you have these like very simple tests, and you want to make sure that you get like exactly the results that you expect. But let's try running this now.
Yeah, even here there might be a race condition still, right? Because we're forking before potentially.
Right, and so we may see we're like missing one of these values, but yeah, exactly.
But luckily, no.
Yeah, so here we got kind of the most expected result, and partly that's because we were doing some of the delays in here. But in a minute, maybe we can go and we can kind of do an example of like for testing, like how you would make sure that was completely deterministic. But so you can see here, we got exactly the same output we had in the naive one. And I mean, that's why the naive one, it kind of was less efficient, but it did largely the same thing here. And when we're playing with these 5 values, it's not like the performance is gonna matter. But yeah, you can, ooh, we got some fun names here. Destroy here. Consumer of worlds.
Yeah.
So yeah, let's try this. And so we see, yeah, we can just add more and more of these values, and just each of them is going to get all of the values.
One use case, which I think Adam did allude to at the start in our first symposium, was we had a Zio Slides app, and we were using this, the hub, to facilitate sort of WebSocket communications between the clients and the server. And this is a perfect use case, sort of subscriptions to a server for Hub, because the number of clients is going to be varying over the course of your application. And I don't know how many people are going to connect to my Slides app and how many people I need to publish the current slide state to up front. And that's going to change as the application goes on. And this is going to make sure that we're not, pointlessly publishing, and we're sort of handling resource safety and closing connections, and as people disconnect, we're unsubscribing them sort of invisibly. It's kind of nice. You don't really have to think about it when you use it in the right way.
Yeah. So I think maybe we can spend a minute on like how we would just make 100% sure there are no race conditions here, and then maybe we can do questions and we can kind of transition to like doing this in more of a streaming context. Does that make sense?
Yeah.
Okay, cool. So again, for most production cases, I think like this is actually kind of what you want. You have asynchronous people who are just joining or dropping off at different points in time, and you just want to pick up with events when you join. But if you need to have very deterministic tests, and like we don't want to like actually use time here, the way you do that is typically with something like a promise. And so like here, we might say, maybe this hub consumer is also going to take one more thing that's going to be like a ref of int, that's going to be like current subscribers, call it. And then we'll say, as soon as we've subscribed, we are going to just subscribers dot update. We'll just say like, hey, we've subscribed, just so you know we subscribed. And then,
ooh.
I'm going to make a little ref here. And I'll pass that in. And then I'm actually also going to make a little promise for myself. And then I can actually pass that here. Maybe I'll just call this like start.
You want to have that on the producer or the consumer?
I'm going to have that on the consumer here.
Okay.
Or maybe, and we call this maybe ready or something. And so in this case, for this like simple example, I'm going to update that, and maybe I will update, I'll update and get it. And then I'll look at that. And then I'll say like, if n is 4, then I'll succeed, and otherwise I won't do anything. And then I'll pass that in here. And then I'll just say, so what I'm basically saying here is I'm telling each of these consumers like, hey, as soon as you've subscribed, update this ref to just say like, okay, one more person subscribed. And in this case, I knew there were 4 of them. Maybe I could have passed it in or something. But as soon as all 4 people have subscribed, then signal that it's okay to go. And then here I have the producer wait for all the subscribers that they're expecting before starting to produce the values. So let's just make sure we haven't made some silly mistake here. And in this case, we see the same thing because we don't really need this because we had the delays, but that's just to show you, like, if you're doing a test and you don't want to use any real time and you want this to be completely deterministic, that's kind of how you can do that.
Maybe if I had a delay to this, we'll see that that's the case.
Yeah.
So yeah, everybody should still get everything, even though it took one of them a second before starting.
Exactly.
And let's just not await and see what happens.
Yeah, yeah.
And I think those first 2 are going to miss the first couple of events. Yeah.
Yeah, exactly. Only the data eater and the info destroyer got the events that time, exactly, because they were being published every 100 milliseconds, I think. So these guys hadn't even subscribed by the time this one had done all its publishing.
Sure.
Okay,
Definitely.
so I think that's a pretty good overview of things you can do with hubs. I guess maybe just a couple of other things I will hit on here before we go to the streaming. So we said there were these different types of hubs. And so actually, and maybe this is kind of good, like both queue and hub review. So in a way, the simplest type of both of these is unbounded. And that just means, I mean, a little bit like the name, it's unlimited capacity, publishing never back pressures. And so this is kind of the simplest version. Like, I guess if you didn't want to think about it at all, like this might be what you would like do because you kind of don't have to make any other decisions about it. The watch out here is that if the producer is faster than the consumers, then the hub can just, or the queue can just keep growing and growing and growing forever. So generally, like there's a little bit of a recommendation of like unbounded queues and hubs are like memory leaks waiting to happen. And really you'd like at some level to back pressure, you'd like something to just stop if you just keep getting that situation versus just using more and more memory and eventually slowing down and blowing up. So I would say these are good either just in like really like simple like demonstration cases or tests or things like that. And there may also be some cases where practically you don't expect it to get that large, but for correctness, you don't have a really reasonable bound you can put on it. So like if you like wait on a ZO promise, that'll kind of get added to an unbounded queue because there's really no way to say like, well, we support 10,000 people waiting on a promise, but not 15,000. But most time, luckily, like you don't have nearly that many. So that would typically be where you'd use an unbounded queue or hub. Then you have bounded ones. And that means, as Copilot is quite correct, that these have limited capacity. So you specify it, like that's what we were doing here, and we said 16. And if there are already 16 values in there, then other producers will back pressure. So they'll just suspend without actually blocking any fiber, any threads, but they will semantically block until space becomes available. And in the case of a queue, space becomes available just as soon as a value is taken. In the case of a hub, space becomes available when everyone who subscribed has taken that value. So you got unbounded, bounded, and then there are two other variants. So there's one called sliding, and this has limited capacity, but this says, well, we're gonna drop the oldest element if full. And there's a decent number of cases where this can be a pretty nice solution. Essentially, anytime that you don't need to be lossless, that you can afford to drop some values, this a lot of times will be the right solution because you end up dropping the oldest value, which a lot of times is like the least relevant value. So you can imagine like maybe this is like some like stock prices maybe that we're like broadcasting to a lot of people, and we only have so much space, but like we're producing, there's new stock prices faster than our consumers are using them. So probably dropping the oldest stock price makes sense, because like if we're getting all these so many new stock prices in so quickly that we can't deal with them, well, we should just kind of drop the oldest ones and we should skip ahead to like the newest ones that have more timely information that we can do things based on. And then the final case is this dropping one, which also has limited capacity, but this time it drops the newest element. So this time, like if the hub has 8 and I try to offer 9, it just throws 9 away. It says, well, I'm already full and you said to drop, so I'm just going to drop that 9. So that is kind of similar to the sliding queue or hub, but the opposite strategy in terms of drop the newest instead of drop the oldest. I think this probably tends to, at least in my experience, be the least commonly used one, because I think, again, if you have to drop something, like typically dropping the oldest seems to make a little more sense, but it provides some nice symmetry. And yeah, I think there may be some cases where you want to use that. So yeah, so those are the different varieties of hubs and queues. Does anyone have any questions on those?
Check in the Discord, but that's a good overview. Any questions? Some questions about, do Erlang actors have unbounded message queues? I have no idea how. That's a good question.
That would be a wonderful question for someone in the audience to investigate and tell us about.
Yeah, because they don't give you the different constructors. Every sort of actor just has its own. Maybe there's a way of configuring that. Probably. Or it'll crash, right? Because it's
let it crash.
Yeah,
I'm not sure that works if you run out of memory, but otherwise, yes. So then the one other thing I just wanted you to at least see is for both hubs and queues, there are actually some additional operators you can use on them to transform the hub or the queue. So if you like look at these hubs, I can actually do like a map on the hub, or I can do a map ZIO, or I can do a contra map. And so these create new versions of the hub or the queue that transform incoming or outgoing elements with some function. And again, that's like a little bit less common. I would say, 9 times out of 10, when you're working with a hub or a queue, you're just going to work with it being a hub of ints or whatever. It's just a hub. It's not one of these fancier ZHubs or polymorphic hubs or queues. But this can be nice in some situations and can allow you to express kind of other parts of your logic flow. So maybe to give a simple, oops.
Can you hear me okay?
Yeah.
Okay.
Totally.
I think I ran out of power on my AirPods, but I think the audio here is
good
enough. So let's say for some reason, we want, I think here we're just stringifying these things anyway, so it doesn't matter. But let's say we wanted our hub to be responsible for turning these ints that are coming in into strings. So I could, if I wanted to, I could do, I'll call it like mapper hub. And that's going to be my hub, and I'll map and I'll turn all these things into strings. And so if I look at this, now I get this fancier type of, I get this ZHub thing. And now it's got like lots of type parameters, which basically these first two are the environments that it uses for transforming the inputs and outputs. These are the errors that could occur transforming the inputs and outputs. And then this is the input type, excuse me. This is the input type and then the output type. So now this hub is going to take in ints and output strings. And so now if these like hub consumers, I don't know if Kit was already ahead of me and updated.
No, I was not.
For them to work with hubs of strings. Now, let's just
But would that be a hub of a string? Because it's the ZHub, right? Maybe we want.
Oh, we need to update our signature. Yes, that's exactly right. So maybe let's. And I think we actually don't really.
We say any string, right? We don't care.
Any string there, I believe. Yeah, let's get some auto compilation going here. Let's see.
Oh, and then we want to use the mapper hub.
Yeah, exactly.
Oh, did I spell that right? Oh, it's slightly sad. It wants. Oh, it found int, but it wanted any string. Interesting. So can we not widen it there?
Let's see. Oh, I think this can.
Oh, we do nothing, of course, right? I think, of
There
course.
we go. Yep.
Okay, good.
And now we can run this again. And so in this case, we were already turning them into strings anyway, so this was not necessarily the most exciting thing. But you could imagine maybe sometimes you want, as part of your queue or your hub, you want to maybe decode or encode some values. Yeah, okay, uppercase.
Well, actually, these are numbers, so
numbers.
wait.
That's not gonna. Yes.
I'll add some exclamation points. There we
go. Exclamation points.
There we go.
There we go. So we can transform outputs that way. We can also transform inputs. Transforming inputs, particularly for a hub, can be more efficient because the input only comes in once versus the output goes out each time to different people. So like here, I could also, let's say I could kind of do this the other way. I could create a hub of strings and I could contra map ints into strings. And I can spell contra map correctly.
Would it potentially be possible? I think we may have talked about this a while ago as well. Oh, well, first, let's fix that stuff. Oh, this needs
these, oh, and then this. Oh, it needs the
I guess we probably still want to map the output as well, though, just so we don't have to change the other signature. Let's see
so I think this is int string. I think it's now just this one that needs to be updated here. So I'll just do that right now.
Okay.
And now this one needs something that can take an int and then
any or nothing.
Let's try this.
Okay.
Yep. And so this is just another way to do the same thing that in this case is a little bit more efficient. And then I think another thing is probably actual, I mean, I kind of wanted to show you how you could transform the types, but I think another thing is probably one of the most useful things to do with this is this can also just be a nice way to like do logging or something here. So like if I wanted to, maybe we go back to where these are both, well, maybe I'll leave this so it compiles, but then I could also do something like, I could do like map zio. So I've got this string and then I could do like zio.debug. Someone took s from the hub and then I could just it's back. Oops.
Oh, I think there's a oops, I added an S at the end. All good now.
Oh, no. I think we're there. And so now we just get like nice little debug messages there. So I think that's probably one of the more like practical things you do with that, though. It's nice to have that kind of flexibility. Though probably if you're really doing a lot with like transforming, like that's another case where like it's nice to go to streams and you get all that nice stuff there.
Mm-hmm.
Okay.
But yeah, I mean, going back to like the reasoning as to why these methods exist and why there is the ZHub, right? It's because we've talked about this a lot in the past. A hub is neither a producer, well, it is a producer of some type, but it's also a consumer of some type. It is what is called invariant. And so it has all the laws, all the sort of the operations that you can get for free whenever you produce values, as well as those when you consume values, right? If you produce a value, you can always then call some function on it. If you consume a value, you can also always pre-process that input, right? And that's if you pre-process, that's this contra map. And if you post-process, that's map, normal, regular old map. And so this exposes all of that. But yeah, it can be very useful in some situations. So it's also nice that you can mostly forget about it and not have to worry about all those type parameters when you just want the normal case.
Yeah. So, okay, so I think from here, we should maybe go back to like some of our original examples, and maybe we can explore how we would do them in more of a streaming context, and how that maybe can give us like a nicer way to write some of these things, and also see a little bit about how like a hub would be used under the hood of these.
There's one maybe question that Gondorn asks, which is, if my hub runs out of capacity because one or more consumers are slow, is there a way to cancel or drop these consumers instead of dropping new elements? For example, provide a way to specify a timeout for how long we wait for a consumer to catch up with the index of the other consumers before we unsubscribe that consumer.
Yeah, so that's part of what you really get as part of this Z managed here, because that would give us the ability to kind of do exactly that, of like when you subscribe, specify logic of like this thing has a timeout, like you're only allowed to be subscribed for so long. Yeah. Okay, so thinking about streams. So let's think about how we would do something maybe similar to our like broadcasting example here, but in more of a streaming context. And so the nice thing about this is, we get to be a little more, a little higher level here, a little more declarative than kind of creating these producers and consumers necessarily ourselves. And so one of the things we could do here is maybe we just initially create something like, maybe we call it like a source stream. And this maybe is a Z stream. And maybe, this will depend on the clock. And maybe this will be like Z string, iterable, 1, 2, 4, 5. And then I think we have something, I think we either have tick or schedule. I should also just bring in the CO stream here so I can get some autocomplete. Right stream operator for this. That. Is it delay or quick delay? Do you remember the name of this operator?
What are we trying to
just like add a certain delay between each one of these?
Sometimes I just do tap and then sleep.
Right. Yeah, that's a very easy one. Yeah, that's a nice way to do it.
Though, a delay or a spaced or something like that.
I'm pretty sure there is. I just don't remember it right now. And so you can already start to see why like streams are nice, of like the logic we had before of like we had this like producer and it was like doing this thing, and then we had to like fork it and join and all this stuff is basically kind of described much more nicely here, of like, okay, this thing is just gonna produce these things as we go. And then we can think about how we would broadcast this. And so we can use this. We'll see there are a couple of variants of this we can use, but the simplest one is this broadcast operator. And so this takes these two parameters, and we'll see these correspond very much to the ones that we were talking about when we were working with the naive and the non-naive hub implementation. Of this one is not dynamic. It asks us to say upfront how many we want to broadcast to. So like here, let's start with just maybe maybe we'll do 4 because we can broadcast to the information destroyer and whatever our other fun one is. And then it's going to ask us for a maximum lag, which is essentially the same parameter that we had with the hub, of like what the size of the hub is. And so maybe we'll say the maximum lag is going to be 16.
Do you know if that's going to be bounded or dropping or something?
It's going to be bounded, yeah. Generally, if you see any stream operator, I think almost any operator really, that like asks you for some size, it's going to be bound unless it very specifically tells you otherwise, because those sliding and dropping variants are they're lossy, right? We could just lose elements there. And so we're not going to want to lose elements unless the operator is specifically saying it, like there's a buffer sliding or a buffer dropping, that like, okay, in that case, we're actually going to lose those things.
Gotcha.
And so if we look at the signature of this broadcast, it's going to give us this chunk of streams, and the size of the chunk is going to be equal to that n that we specified. So like here we specified 4, so we're going to get a chunk that has 4 streams, and each of those streams is going to get all of the elements that went to the original stream. So here, if we wanted to, we could call this streams, and this is a chunk of streams. And then we can do whatever we want with the streams. So maybe we should make some operators to do some fun things with the streams, or relatively fun as for at least what we're doing. So let's take our little consumer, and let's maybe think about how we make a kind of streaming version of this. So maybe I'll call this like consumer stream, maybe. And maybe I could actually make this, maybe I can make it like a pipeline, just so we can like play with combining some of our concepts. So maybe I could give this a label. It's a string. I guess I need to type that because that already existed. It's okay. And I think maybe I can make this pretty simple of, well, one, I'm not going to want to make it a Z. I'm going to want to make it a Z pipeline. So I'll do Z pipeline. And then if I go back to this, this basically takes an environment it uses, which would be the console. This one I think we'll say is not going to fail with any errors. And this one I think is going to take, I mean, maybe we can even make this polymorphic. And so it's going to take an input of type A, it's going to put out the same type A, it's going to use the console. And so this one I think we can do pretty simply of like, I think we have a, yeah, we have a map ZO here. And so that's going to give us an A. And then we're just going to print it out and return it. And so now I think, so we've got this chunk, and maybe we're going to say, maybe I'll call it like consumed streams is going to be a chunk that maybe is going to have the first streams, and we'll send that to consume. And now we got to just go back and, okay, so we'll start with our boring names. So we got our logging framework, and then we'll send another one to database writer, the data eater, info destroyer. Nice work, Copilot here. So, and let's see, why is this not happy here? Let's see.
Required a sync instead of a pipeline?
That's interesting. Oh, okay. Well, we can do via.
Oh.
And why is this pipeline?
This is overloaded.
Oh, I think this, I think we just need to specify the type parameter here.
Okay.
So I think we can say these are what, ints, I think. And maybe I could just specialize this. Maybe I was making too polymorphic there. Oh, and we need to do or die here. Okay. So now we've got a set of streams back. And then we've got a little bit of flexibility here of like, how do we want to consume these streams? Like, do we want to consume one at a time? Do we want to consume in parallel? I think here, like, yeah, probably just consuming them all in parallel is correct. I don't think that's actually valid syntax, but I think that's like Z stream dot merge all unbounded. streams. And let's see. Oh, and I think it's expecting like a lag, so I'll just found chunk. Let's see. Oh, is this expecting variable arguments? It's expecting variable arguments. Okay. So do that.
And just 16 again.
Okay. And now, right, then we're going to
I see.
drain this guy. Dot run managed. Oops. Now let's see. Oh, I think I just did run. Okay. And so let's try changing run to use the stream example. Oh, it already is, but what do we, oh, and then we can just, now that we've got that, use that. Actually, let's see this.
Oh, it's just a managed now. I see.
That. Just put that. Okay, perfect. Okay. Okay.
Oh yeah, I think they're in a slightly different
Slightly
order.
different order, right? Right, which is, yeah, that's part of the contract here of, yeah, we're doing these things in parallel, so they can be in a different order. But so here's kind of the streaming version of the same thing. And internally, this broadcast operator is still using a hub. And I think we even saw how the parameters that went into this broadcast are the same ones that go into the hub. But this definitely is a nicer, more declarative way of doing the same thing, where we're kind of saying more about what we want to do versus how we want to do it.
Mm-hmm.
So this is this broadcast operator that you could think of as being like static in a way of like, we said up front we wanted exactly 4 subscriptions. The other thing we can do here is there's a variant of this called broadcast dynamic. And so this one, we don't have to say up front that we want 4 streams. We can just say we want the ability to create more streams on the fly. And so this one, if we look at its signature, it's going to give us a ability to create a new stream here. So every time we evaluate this stream, we're going to open a new subscription to this thing. And so here, like we probably, maybe we'd actually like, it'd be easier to call that subscribe. And so then if we wanted to, each of these, I don't think here it's going to be that different, but see now, instead of just getting this like chunk of streams, we get this thing that we can subscribe to. And
But that would return a managed, right? So we need a flat map on those to get a chunk of managed.
let's do that. It's auto compilation. Okay, so I think we're good here. Let's see. So if I do stream example dynamic up here.
Oh, that's I thought subscribe is now a method though. How does that? Oh, it's a Z stream. I'm sorry.
It's a Z stream. So every time we call it, it's just like a ZO is a description of a workflow, and we can evaluate if it's like ZO print line, like every time we call it, we'll print line again. Here, this is a description of subscribing to receive these values. And so we call it 4 times, we generate 4 subscriptions, and we'll see those results here.
Yeah, one of the cool things about streams that is maybe for me it was a little difficult to wrap my head around at first is that they are a superset. They can do resource allocation and release as well. They represent the whole opening a stream and shutting it down when you're finished. So it's kind of cool that they can subsume subscription logic inside of them.
Yeah. Yeah. So let me show you one other thing with streams that I got a question about recently that I think is something that like you can kind of, I guess you can run into if you're not familiar with. So I would say the most common way to work with hubs and streams is just hubs are used internally, right? You use this broadcast, use broadcast dynamic. I mean, we look at this and you don't see a hub anywhere at all. It's just more, it's used internally. The other time, though, I think you can see it used is there are times that you want to interface between a streaming and a non-streaming interface. So like this was, I think, really nice and pretty in a way because everything was streaming, right? Both the producers that were going into this broadcast dynamic and the consumers that were consuming the values were all streams. And so everything could take place in this like nice world of streams. But sometimes you have a situation where like the producer is a stream, but then the processes that you want to consume it are maybe more traditional non-streaming ones, or like the fibers that we looked at the beginning. And so one of the operators you can use for that, so maybe I'll do all this like stream example 3. So we can do this source stream, and there are a couple of variants of this, but there's this run into hub. I think there's actually even another one that's even simpler of into, okay, I guess we can run into hub. So let's like look at this for a little bit. And so here, I'm going to create a hub. And then I'm going to take that source stream and I'm going to run it into the hub. And so the thing that can, I think, trip people up here a little bit is, well, is exactly this. That's like actually a perfect setup. So if we look at the signature of this run into hub, it's like slightly different in that it takes this take thing. And I think that's something that is actually used a decent amount in the streams, but that people may have seen a little bit less of. And so I think this can throw people off a little bit. And so all you want to do here is like right now you're getting this compilation error, but all you want to do is you just turn the type of the hub into what it's expecting. So like this will be a take of nothing int. And what this take thing does is it represents the different results that you can get from trying to take from a stream. So and so I think if you go back to some of our other talks about streams, they're basically like 3 cases that you can get from taking. So you can either get a chunk of values, right, which says, hey, I got this chunk of values, maybe there are more in the future. I can get an error, or I can get an end of stream signal. And so that's all this take data type represents. And we can even, I mean, it's literally what it's wrapping. So it says like, hey, when I take, I can either get a success, this just got a chunk of values, or I can get a failure. And that failure can be one of 2 things. It can either be a sum with an actual E, so that means an actual error occurred, or it can be a none, which means there's no error, but the stream is just done. It doesn't have any more values to give to you. And so this take thing just wraps those different possibilities up into one data type and just gives us some nice operators to use to work with them if we want to. And so the reason that run into hub has this signature is that the people who are consuming from this hub, they need more information actually than just an int. Because if they get an end of stream signal, they don't want to just be sitting around, and they may not just want to be interrupted. They may want to be able to observe that, hey, the stream is done and I need to go and do some cleanup of my own, or an error occurred. Well, maybe I need to do some error handling. So this run into hub runs it into a hub that has all of that information on what these values are. And then if we want to, we can kind of unpack those values and do whatever we want with it. So here, if we wanted to, let's see, can I do, I guess I can't quite do the hub consumer, but let me do like hub.subscribe .use queue. And then I could do like dq.take .flat map. And so then I can start to match on these. And so like a really simple thing I could do here is maybe we say, just do like, yeah, and remember, let's remember this could have two possibilities, and maybe we should actually handle both of them. So yeah, we could do like print line, stream done, exactly. Then we could print error, and then if this is, I think this one, these are going to be causes, so this will be slightly, I think, more complicated. But let's just do this case first.
Oh, I see.
Yeah. So here, so this is going to be like a cause. And right now, just at least we can deal with the cause in a second.
Yeah.
Yeah, exactly. Okay, and now we can do stream example 3. Let's see what we have going on. What did we do wrong here? Oh, we need to focus. When we get here, we got a take, success, chunk. Did we do something silly here?
That seems odd to me. I
Seems
think
odd.
we're handling every case, right? I mean, it's exit can't be something else. And if it does succeed, it has to contain a chunk, and that's what it says it has. I don't know. We get another case where it's
That was 140.
huh?
So let's try it. Maybe we always could find bugs with their bugs. Let's see. Well, that's very interesting. I mean, maybe we can just do a case. Yeah.
It's odd because it is a take unless the types are different somehow. It just got a success? Oh, because we're saying
Take. So that's very interesting. Yeah, because this should be typed as a take.
oh, I think we found a bug.
I think this is something we're going to have to look at offline here.
Yeah, that makes sense. I can imagine how that's happening.
Correctly. Yeah,
because
so
it's definitely
yeah, so we will take a look at that offline. And that's why it's nice to do some of these things. But anyway, we can see here. Other than us finding bugs, the main takeaway from this is be aware this take data type exists, and if you do something like this, run into hub, just like it expects a take, just use that as the type of the hub, and then it'll actually give you this ability to deal with all the different possibilities of the values that the stream produced.
Yep. Could I quickly mention my favorite operation on hubs?
Yeah.
That would be to, and it's very much sort of what we did in those very early Zymposiums.
Yeah.
But it's, if you do just have a normal hub like this, generally you have some service where you're going to have a hub as one of your parameters, and you're going to broadcast to that hub, publish to that hub when people do things. But you might wish to expose a streaming interface, and my favorite thing is just zstream from hub, and you just pass the hub in there. And this gets you back a stream. But the very nice thing about this is that when you actually execute this stream, is that sad for some reason? Shouldn't be.
Well, I think this expecting this to be like run into a ZO, so this needs to be like run drain or something.
Oh, yeah. Sorry. Yeah. Or I could just create.
Yeah. You can just describe it exactly.
Okay, exactly. And does there need to be that might be a new parameter? No, okay, it was just that.
No.
So what's really nice about this is that when we do run the stream, that takes care of opening the subscription. And then when the stream is, whenever this effect is either interrupted or fails or completes or what have you, this subscription will be released. And this is basically what we've used for connecting over WebSockets. Every time a user connects to our application, we basically just return a stream that we run and then broadcast all the results over the WebSocket. But the second that user disconnects, the stream will be closed and they will be released as a subscriber from the hub, sort of invisibly, because of the fact that that stream contains the subscription and release logic. So only by actually executing the stream, it's another sort of referentially transparent value. It's very nice. So yeah, I find like that's mostly how I've used hubs, is to create them, to publish to them, and then to translate them into streams and then stream out their values, I guess generally over WebSockets or to anything else, because it nicely handles the subscribe stuff for you. You don't have to do that manually. You just deal with the stream, and you can do things, stream.take 10 values, for each console.println or something like that. Which is pretty nice, because once this has processed 10 values off of the hub, if I do hub.publish 10, repeat, and 20, once it takes 10 values, I think I've misspelled that. There we go. Once it takes 10 values, yeah, we'll do that. I'll do forever.fork. Once it takes 10 values, it's going to shut itself down and release the subscription. So yeah, translating hubs into streams is my favorite way of dealing with them.
Yeah, and well, I think that's really nice, because that kind of closed the circle of, if you think of the things we covered, we started with just talking about how to use in this non-streaming world, and we saw you used publish and subscribe. Then we talked about like a fully streaming world where you're going from a stream, broadcasting to streams. And we saw those broadcast and broadcast dynamic operators. Then we saw going from streaming to non-streaming, which was that run into hub that we went over. And this is like the last part in this, like, you can think of it like a 2x2 matrix of, if you're going from a non-streaming to a streaming interface, then that Z stream from hub is like the perfect one for you. So yeah, I think that's like a really nice way to put everything in a nice box.
Yeah, totally. We did it. We explored the graph. Explored the quadrant. Every quadrant. Okay, well that was fun.
Yeah.
It's a deep dive into hubs. I wasn't sure if we'd take the whole hour and a half, but no.
Yeah, we always find a way. We find a way.
Somehow, always, it's exactly an hour and a half. We don't really. I don't know how that works out. It's kind of weird. But anyway, I hope that was fun. If there are any questions we didn't get to, please just post them again, and we can maybe take them offline. Or if there are any we have a few minutes. Oh no, okay, I'll repeat the question. Okay, oh yes. I said I was going to skip this question, come back to it. Thank you for reposting it.
Yes.
Yeah. So this is a question about streams, but maybe it makes sense here as well. How can you do something like having a primary stream and a secondary stream? And when there is no data on the primary stream, it then falls back to the secondary stream. But if the primary stream comes back, then it goes back to it.
Yeah,
I'm not sure if that's built in. Maybe it is. There are many stream operators, so maybe it is. But I think, yeah. What about that?
So I think there are a couple. So I think it can depend a little bit on like the exact semantics you want. But I think probably the most the simplest one that would do that would be one we used a little bit, which was this merge operator. And so this one you can think of as kind of the race equivalent for streams. So this one just says essentially try to pull from both streams and just pull values as long as they're values from either stream. And so if one stream doesn't have values, but the other does, then you'll kind of pull values from that one. So that I would say is the like most like simple version of that. It sounds like that might not be like exactly the semantics you want of, you know, you kind of want to like prioritize the other stream. But I think that may get you what you want in a lot of cases. If you want to do fancier things, one of the most useful operators for doing that is there's one called, let me see if I can find the,
Oh, and they said that primary does have the priority in this case.
right. And so I think what you need to answer a little bit for yourself there is like, what does priority mean? Or another, and maybe a more specific way is, how long do you want to wait for it, assuming that it doesn't have a value, right? Because if we think about it conceptually as going back to some of our other discussion about streaming, streams give us the ability to pull from them. So like, I think the most helpful way sometimes in these problems is like, first, like state what we're trying to do in words. And so it sounds like we want to say, try to pull from primary stream. And then conceptually we say, well, if we can't pull, then we want to pull from the other one. But I think one thing we have to like think about a little bit here is like, like the way this streaming works is either there are some values right now, or there's just this effect, there's this pull that doesn't return yet until it does have more values.
It blocks semantically, right? So yeah.
Right, semantically blocking until there are values. And so I think what we would need to do is we would need to have some concept of like how long we were willing to wait for there to be values in the primary. And then we could basically like switch over, we could try to pull from that. And meanwhile, we could kind of hold on to that pull we did, and we could like wait for that to return. So I think we could definitely implement an operator to do that. I think it's a little bit specialized. So I don't think there's one off the shelf for that, but that's how I might think about that.
Yeah, definitely. I don't think it's out of the box, but that is an interesting one.
Yeah,
for sure. But yeah, very specific. There would be potentially many implementations depending on exactly what you wanted, as you said.
Yeah, exactly.
But cool. But yeah, if you try exploring that and you need some help, we'll definitely share it. I'm sure.
That's that'd be super fun.
That'll be
we're still looking to do one of these sessions where we kind of, or maybe more than one of these sessions where we work through people and building out their own applications. So if anyone would be interested in doing that, that'd be fun to do together.
Totally. Yeah. Or if you have some juicy ZO problems that we can run together, maybe, we could try a hand at this one or collect a few and see how many we can get through. Yeah. Open issues in our, in the repo I posted, or just us, but I wanted to try that. So, okay. Well, thanks Adam for walking us through.
Thank you so much, everyone.
Thanks everyone for coming.